All right, so these are some diagrams that show, or I guess they're graphs, that show how energy changes in a reaction. So basically on this first one, endothermic, we start out with not a lot of energy because energy is right here. And then as the reaction goes on from reactants to products, our energy is a lot higher. So in an endothermic reaction, we could say we're gaining energy. Now, on the other hand, an exothermic reaction, we start out with a lot of energy. It's all built inside of the chemicals. Then once the reaction happens, at the end of the products, what we're created, we've got a whole lot less energy. So this from the reaction is, I guess we could say from the first to the last, it's losing energy. Where are we losing it to? Well, it's being given off into the environment. So this one, heat, is normally the case, where this one is cold because it's taking in energy. It's storing it inside. So it's not being released to the environment, okay? So our laws of conservation of energy, it says the law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. This means that in chemical reactions, the total energy of the reactants must be equal to the total energy of the products. So an example here, we've got methane, which you don't have to know what that is, but the common name for this is methane. And then oxygen. So we take a gas and we give it oxygen, and when we do that, it creates water and carbon dioxide, okay? So what is created here is fire. I guess that's the energy that's given off. It says in a combustion reaction, for example, some of the initial chemical energy is stored in the bonds of the fuel. So a lot of the energy in our reaction is stored in the bonds of CH4. It's released as thermal energy, and however energy is not destroyed, it is converted from one form to another through a chemical reaction. So it's stored inside the bonds. When we give it oxygen, it releases it. When it releases the energy doesn't get lost, it just goes into the environment, so other things could absorb that energy. All right, so that's sort of what the law of conservation of mass means. Your energy always changes from one form to another. Our law of conservation of mass, this is basically telling us that if we start out with so many grams on one side, then we should have that same amount of grams on the other side. So our reactants, the mass, should equal the product's mass. So if we have, in this example, they have 32 grams of sulfur and 56 grams of reactants. If we add those two together, that gives us 88. And that is what we have right here. So 88 grams of FeS, when they connect together, they would have that as a mass. Why is this important? Well, basically mass can't come out of thin air, and we don't just randomly lose things. Things don't disappear like you have something on a table, I don't know, a pencil, and all of a sudden it's vanished into thin air. That's not the case. So these things that occupy space, have mass, they are going to be contributing to the products, which we have as FeS in this equation, okay? So they're giving us an example. They want us to do an example of law of conservation of mass. So let's try this one out. It says, consider the following reaction. So it's Na, which is a solid, and Cl2, which is a gas, is reacted together to give us NaCl, which is a solid. It says, what mass of chlorine gas must react with 30 grams of sodium? So as I read through the question, I like to write the the grams over top of the elements. And Na, if you guys don't remember, is sodium, to produce 50 grams of sodium chloride. So we got 50 grams of sodium chloride. So they're asking us how much of Cl do we react? Well, we know that reactants is equal to our products. So the mass of our reactants is equal to our products. So if our products are 50 grams and we have 30 grams plus something, we just got to figure out what that missing piece is. And that missing piece would be the mass of chloride. So 30 plus what gives us 50? The answer would be 20. Okay. Another way of doing this, you could go 30 plus x is equal to 50. And then you could solve for x if you would like to, where you take 30 to the other side because that's a minus. So it becomes x is equal to 50 minus 30. And then we figure out that that is 20. So whatever way you need to do to figure that out, but basically that's as simple as the law of conservation of mass is. We're just solving for the missing piece. These reactants will always add together to make the products. It says another implication of Lavoisier's law is that you cannot, so he's the one that came up with the conservation of mass, you cannot have more of one type of atom on one side of the reaction compared to the other. So there must be equal amounts of everything on both sides, as matter cannot be destroyed. So when we're talking about matter cannot be created or destroyed, we're talking about we need to have a balance of atoms from one side to the other. It says, due to the law of conservation of mass, chemical equations must be balanced in order to be properly written. This is accomplished by adding coefficients in front of compounds to indicate how many molecules of each must be present in order for the reaction to occur. So a coefficient, what they're talking about here is this number 2 in front and this number 3. Those are in front of there to sort of balance out our reaction. So when we need to balance it out, we need to have the same amount of atoms on one side to the other. The only thing we can do is add these coefficients. Okay. So there's a bunch of examples here, and I'm going to show you through example on how to do this. I will do this one that we have right here on the side, and then we can move elsewhere to balance. All right, so I'm going to do number 1. This is number 1 that we see right here. We're just going to do it on the side here because it does take some space. Maybe you can already see some of this in your head, like me looking at this, I could already see how to balance it, but starting out, you'll have no idea what I'm even talking about. But once you get good at this, you might be able to do some of them without even writing numbers down. So our very first step here for balancing equations is that we need to balance the sides. So balancing the sides, to me, I always draw a line down the center because this left side is going to have to equal the right side. Okay? My next step is I'm going to tally up all of the elements that exist on each side. So for this one, we've got Na on this side and we've got Cl. Notice I'm not putting this 2 there because that 2 is actually not part of the element that's telling us how many of that element is there. So we're really only worried about the elements that exist. So those are the elements right off the periodic table, no numbers involved. Something else to note is that if you have Na and Cl on the left, you should have Na and Cl on the right. If for some reason I had NaCl and H or something, well, there's something wrong because we need to, the products and the reactants should be the same. They should be the same elements. And I like to write them on the same level, like Na across and Cl across, just so that it's easier to see this as we're doing it. All right, so my next job here is that I need to tally up how many of each of these I have. I knew this was going to be trouble when I'm on the side here. I guess I can do this. So I need to tally up how many I have, and to figure out how many I have, it's a pretty, hopefully, simple process. What we do is we look at the number in front and the number behind, okay? So if there's no number in front and no number behind, then it's 1. Cl, there's number in front, number behind. There's no number in front, but there is behind, so that's a 2. This one, number in front, number behind, and there's no number behind Na either, in between the Cl, so these are both going to be 1. You don't put 0. Some people want to put 0. There's 0 of them. Well, there's not actually, because we would never write it even if there was a 0. There would be no point in us even writing Na and Cl here. We would just not even write the symbols. So there is 1 there if we've wrote those symbols out. Okay, so now if we look at the left side versus the right side, we can notice that our NAs are balanced. So our NAs, they're both 1. They're balanced. Our CLs, on the other hand, they're not balanced. So our CLs, there's 2 on the left and only 1 on the right. So in order to balance this out, we can never take stuff away. We can only add. And where we add is right here. So these numbers, these little spaces I wrote, those are where we can add. That's all we can do. All right, we can only put numbers in front. So if we have a Cl, 1 Cl here, there's no number there or in front, then we are going to have to write a number in front. And when I'm going to write this number, which is 2. Okay, so that 2 in front tells us something. Get rid of those. It tells us that I've got 2 NAs, but it also tells me I've got 2 CLs. So this number in front, this tells how many we have of everything behind it. So that 2 is like multiplying by everything, all of the elements that we have there. So by putting that 2 in front, instead of 1 there, now we have 2, and Na has changed to 2. Okay, because it's saying we have 2 of everything behind that big 2, so we've got 2 NAs and 2 CLs. All right, now these are balanced, good. But our NAs are not balanced anymore. Now we've got a 2 here and a 1 here. So we've got to do something about that. So now we go back to the left-hand side, and we need to get 2 NAs on the left. So to get 2 NAs, I'm going to put a 2 right here. You could erase. I guess I shouldn't be. There we go. So, sorry. So we've got 2 on both sides. We got 2 NAs and 2 NAs, 2 CLs and 2 CLs. So it's balanced, okay? That 2 right here is saying there's 2 of everything behind, which is just NAs. There's nothing on this CL2 line, so we don't put 0 there. If we have nothing to write, it becomes a 1, all right? Because everything that we have, those big numbers, those coefficients in the front, they're basically multiplying by the small numbers. So for this one, 1 times 2 is 2, which we've got, okay? If we put a 0 there, it would be 0 times 2 is 0, and that wouldn't work. Okay, so if you don't have any number to put on the line, then we write a 1. All right? So that's how we would do a balancing equation. I'm going to try the next one with you. Just let me get off of this. Just going to copy this into a place where I can actually write. I guess I was in a place I can write. Ah. Okay, so I'm not sure if I can make this bigger. It's fine. I'm just going to write it out anyway. That makes sense. So for here, we've got K plus O2 gives us K2O. All right. So again, our very first step here, whenever we do a balancing, draw a line down the middle. I don't know if that's something that my teachers ever taught me, but it's something that makes sense to me. I like to split it. All right. So now we need to tally up all of the elements we have. So on the left-hand side, we have a K and we have an O. On the right-hand side, we should have a K and an O. Okay. Now I need to figure out how many we have there. So when I'm doing this, remember we're looking at basically the number below, and the numbers below. So the ones that are right below that element, they're called subscripts. Those will tell us how many of the element we're starting out with. So for K we have 1, and for oxygen we have 2. On this side, our K has a number 2 below it, and our oxygen has no number, so that would become a 1. All right. Just gonna get rid of those little greens. All right, so now if we look at our balance, we do not have it balanced. We've got 1 for K on one side, and the other side has 2, and then our oxygen's 2, and the other side's 1. So we're gonna have to balance this out. So how we would do this, I guess we can start with the Ks. No, let's not start with the Ks. So our Ks are not where I would start, and maybe I'll start with the Ks just so I can show you why I'm saying don't start with the Ks. Sometimes this is a little bit of a trial and error, and you'll see when we start with K. All right, so we start with potassium. We have 1 on this side and 2 on this side, so we're gonna need to put a 2 here to get rid of that to make it 2. Okay. So now the Ks are balanced. Now if we move on to our oxygens, we got 2 here and 1 here. So to get 2 on this side, we're gonna have to put a 2 in front of this. Some people will try and put a 2 down there, but we can never add subscripts. We can only add those coefficients, so those big numbers in front. All right, so that 2 in the front is gonna change our oxygen to 2, but what it's also going to do is change our potassium to 4. And why is it 4? Because this 2 times 2 gives us 4. Okay. So now our oxygens are balanced and our potassiums aren't. So we've messed ourselves up. Now we've got 4 on the right and 2 on the left. So something we could do here is we could take this 2 and we could make it 4. So we've already changed it once, but now we're gonna have to change it again. So now we've got 4 Ks and we've got 4 Ks on that side and 2 and 2. So it works out. It's balanced now. We've got 4 and 4 and 2 and 2. The only reason I'm saying I would have started with oxygen is because then we wouldn't have to head back to potassium. But you can always go back and erase and keep going back and forth to balance it out until you get the proper answer, I guess. I'm going to try one more here with you. Oops, I'm not in the proper spot. Let's do the bottom one here. If I can paste it here. Okay, so our question here, we've got Bn plus Cl2 gives us BCl3 and N2. So first step, always draw a line down the middle. Second step, start to tally up the different elements that we have here. So we've got boron and nitrogen and chloride, okay? I like to, like I told you before, even though it goes boron, chloride, nitrogen, I like to keep it in order when I'm tallying, just so I can easily see like across, oh, this is nitrogen, oh, this is chloride, oh, this is boron, okay? So that makes it easier for me, and that's why I like to draw it that way. Our next step here is tallying up everything we have. We've got 1B, we've got 1N, because there's no numbers below. And then we've got a 2 for Cl because of that number. For the other side, we've got 1B, because there's no number below. We've got 2 N's because of that number, and 3 Cl's because of that other number, okay? So if we look at this right offhand, our borons are balanced, they're 1 and 1, but our others are not. So what I'm gonna do is I'm gonna try balance my nitrogens first. So we've got our borons, let's do our nitrogens. We've got 2 nitrogens on the right-hand side and 1 on the left. So our 2 nitrogens, I'm gonna put a 2 in front of there to change our nitrogens to 2. By doing that, we also say we're gonna add 2 to our boron, okay? Because that big number in front, remember, it goes to everything behind. So that is what we have there. Now, our next step is I'm going to balance the borons. So our borons, there's 2 on this side, there's 1 on the other. So I'm going to put a 2 in front of here. By putting a 2 in front of there, that's also telling we have 2 of Cl3. So really, how many Cl's do we have there? We have 6, because it goes 2 times 3. These are multiplied, which gives you 6. Okay, so big number, always multiplied by that small number. So we've got 6 chlorides. So now our borons and our nitrogens are balanced. Our chlorides, not so much. We've got 6 on the right. We need to get 6 on the left. And we've got a little 2 there. So we got to go, which number are we going to put in front? So 2 times what gives us 6? Because that's what we want. We want 6. And the answer is 3. Because that 3 times 2 will give you 6. Okay? Oops. So now they're all balanced and we've got it. For you, when they have these little lines here, sorry I didn't put those. These lines that we didn't put a number on, we would just put a 1. If you saw an equation that was like 2Bn plus Cl2 gives you 2BCl3 plus N2, that's right. I'm just telling you, you don't have to put a number there if we don't have a space, but those spaces I like you to write in that 1, just so you're getting in the practice of knowing that that is 1. Okay? So let's go back here. So there's some other examples there. I'm not going to do all of them, but I'm going to maybe stop there. So here's some practice ones to do, and then some word equations, which I'll get to in our next video, I guess. So try some of those out on your topic 6 question sheet, and please don't hesitate to get in contact with me if you need any help.